Hi, Dr. Lyons here, of course. In this video, we're going to talk about how this hand pump works and some of the experiments that one could do in a mechanical engineering lab class that would include a hand pump like this. Enjoy. So I'd like to give a little overview of the different parts of this pump and explain how it works. The major parts that you can see on the outside we'll call the pump handle. There's a lever arm. There's a piston rod here. The main body of the pump is an extruded steel tube. On the top of the tube is a casting and a fitting for connecting all of the pumping mechanism to the tube. There is a piston inside of the pump, and I've gotten somebody to machine some slots into the pump so that we can actually see what's going on inside. The pump will not work with these slots in there. Down here, if I can get this to come up into one of the positions right here, you can see the piston that is connected to the piston rod, and it is a plastic disc with a hole in the middle of it, and at the top of the plastic disc is a metal washer or flap valve that is pressed onto the plastic disc by this spring that you see on the top. And in the, can't really see it with the lighting in here, but within the center of the plastic disc are some holes cut out. The other flap valve is in the bottom of the piston cylinder. We can see just barely, we can see the holes that are in the bottom, and you can hear that little disc in the bottom moving. When I tip this up, it's going to fall down and you'll hear a little click. So the way the pump works is when the piston is in its down position, which means the handle is all the way up and submerged in water, then this section of the pump will fill up with water as long as it's submerged. When the piston is raised, that's going to create a lower pressure below the piston than above the piston, and the flap valve in the bottom will lift up and water will come in, filling up the chamber behind the piston as it's raised. So in the top position, the bottom of the cylinder is full of water. Now, when the piston is lowered again, the water pressure forces the valve at the bottom closed, and as the pump continues to move down, the water pressure builds up, and water pressure lifts the metal flap on the top up against the spring so that the water moves from the bottom section to the top section of the piston. Now we've got water above the piston and below the piston. So when I pump this again, it lifts water higher above the piston, and also again water is pulled into the bottom section of the piston. So when this pumps enough times, eventually we move one slug of water by another into the chamber until we get to the point where water is actually coming out of the top with each pump. So yeah, that's basically how this particular pump works. It's similar in design to a lot of other hand pumps. I particularly like the fact that there's a spring on this top flap valve to keep it closed when the pump is just sitting and not being pumped, and that will help prevent fluid that has been pumped above the piston from seeping down through the holes into the bottom section, so that it doesn't take as many pumps each time to prime it. Of course, after we let the pump sit for a long time, there is a lot of leakage between the plastic disc in the piston and the sides, and also through that flap valve. So if you let the piston sit for a while, any fluid that's above the piston will eventually seep back down to the level of the water in the bucket. Lifting the water involves a potential energy change. Let's talk about how to estimate that. According to the pump manufacturer, each pump of the handle will pump about 2 ounces of water out of the nozzle. If we want to get a sort of a theoretical estimate of how much work that requires, then we have to consider how much water is being lifted with each pump and how far that water is lifted. So if we move about 8 inches of water up about 1 inch, then we've changed the amount of potential energy associated with that water. So to determine the potential energy change, we need to know the mass of the water that's lifted with each pump and the distance that that's lifted. So if we have a mass at one height and we move it up 1 inch, there's a potential energy change associated with that. One can assume that the distance that the water is lifted is equal to the distance that the pump piston arm moves with each step. So if the piston starts at its bottom point, we can determine where that piston pin, connecting pin is, and when we raise the piston, we can determine how far it moved, and the difference between those two positions on the tape measure gives us an idea of the distance that the water was lifted. Estimating the amount of water that's lifted in each pump is a little more challenging because of the change in the geometry of the system. But for a first approximation, we can measure the distance from the water level, which in the bucket I'm going to say is right about here, to the exit port position on the top of the pump. Now, if we assume that that is the length of the water column, and we know that the diameter of the inside of the piston, we can determine the cross-section of the water column, and the cross-sectional area times the length of the water column will give us the volume of water lifted in each pump, and the volume of the water times the density will give us the mass. It's a little more complicated than one might expect at first glance, because not all of the water in that water column is lifted, say 2 inches with each pump stroke. Because some of the water is at the very top of the water column when we start to lift, and it exits, and so it doesn't take much work to remove that first little top layer of the water. So not all of the water at the top gets lifted 2 inches. The other thing is that some of the water that gets lifted starts off below the surface of the water in the bucket. Assume that the potential energy associated with the water leaving the tank is equal to the potential energy change of the water that's entering the piston. Then those two quantities will combine so that the total energy, the total potential energy of the system can be modeled by knowing the volume of water that is above the tank at the beginning and the distance that that volume of water is pumped with each stroke.
One thing that might be interesting to investigate is how does the speed at which we move the pump handle affect how much water comes out with each pump?
One of the experiments that you can do with this setup is to examine how the pumping speed affects the amount of water that comes out of the pump. The experiment could be conducted simply with just sort of a qualitative measurement of the pumping speed by moving the handle slowly and catching the amount of water that comes out of this spigot right here and weighing that or measuring it volumetrically, and then repeating the experiment, pumping more rapidly, and again measuring the amount of water that comes out at the different speeds. If you want to get sophisticated, one can put a tape measure at the top of the pump and with a video camera actually record the time it takes for the pump handle to move from its bottom position to the top position. If you can measure the distance that pull rod moves, then and the amount of time it took to do that, then you can calculate a velocity for the pumping piston.
It's also possible to measure the work required to pump water. How do we do that?
Another experiment that we can do with this particular setup is to measure the amount of work that's required to pump the water. An estimate of the work can be obtained by measuring the distance that the piston travels times the force that it takes to move the piston. If one wanted to hook a scale to the end of the lever arm, then one could measure the force with the scale, one could measure the force required to move the lever arm a particular distance. Kinematically, that's going to be a little bit of a challenge to do with simple tools just like a tape measure, because the handle doesn't travel a straight line. And then the geometry is such with this 4-bar linkage that we'd actually have to do a kinematic analysis to calculate the force that's applied here at the piston rod based on the force here, because the length of the lever arm changes as it lifts, and the position of the pivot point actually moves towards the piston when the handle is in its bottom position. It's about maximum distance from the piston when the handle is horizontal, and then it moves back towards the piston. So the static analysis is actually something that one could do with some experience with statics and kinematics. But a simpler way to actually measure the work required is to just disconnect the lever arm from the pull rod, so now the pull rod moves freely. And I'm going to put this little hook into the top, because if I let go of the pull rod, it has the potential to fall down into the pump. Okay, so now the pull rod is in place, and that little thing is going to, that little loop is going to prevent it from falling all the way down. Then I can take my scale, and this is just a simple fifth scale, and pull the piston rod up. The scale will indicate the force that was required to pump that. This was about 5 pounds to do that. I can use the scale to measure the maximum force was required to pull the rod up. I can use a tape measure to measure the distance that the pull rod moved, and the force times the distance. It gives you a measure of the work that was required to pump the water out. Now, of course, while you're doing this in the lab, the bucket's going to have water in it, and someone will have to catch the water to avoid making a big mess. So, of course, someone with a tape measure and a video camera could measure the speed at which this pulls by recording the time it takes for the piston rod to move a fixed position. So yeah, those are a couple things that we can do with this little system. It's a nice self-contained pump, and I like it a lot for instructional purposes.